Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be taking a look at entropy from a statistical mechanical perspective. So this means we're going to take a step back from the big scale and focus in on what entropy looks like at the small scale. So entropy, we often will describe this as a measure of disorder. So if something is very disordered, we say it's very entropic. If something becomes more disordered, we say it's favored by entropy. And this actually works fairly well, but there's a couple nuances where it doesn't quite uh, act as the perfect description. A much better description is that entropy is a measure of how many options the system has. A system really wants to be able to be as flexible as possible and hates being constrained. And it's this idea of matter and systems wanting to spread out and energy wanting to spread out that's really encapsulated by entropy. However, it is worth noting disorganized systems tend to be much more spread out than more organized systems. And we can really encapsulate this idea of the keeping entropy as a measure of how open the options are by looking at something called the Boltzmann formula of entropy. In this case, what we state is the entropy of the system is going to be based on two key parameters. The first is our old friend, the Boltzmann constant, which, just as a reminder, is the ideal gas constant divided by Avogadro's number. And then we've got the natural log of something called the microstates. And the microstates is literally how many different ways can I organize a system and still get the same properties. So for a given state, how many different ways can it be organized? So let's say I'm going to go ahead and put a number of gas molecules into a 4 angstrom by 4 angstrom container. And we're going to assume that we can only get one atom per every square angstrom, which is about right for the size of atoms. Now I can go ahead and increase the volume of this container from 4 by 4 to 4 by 6. So we'll be seeing this increase of volume, and we can look at what this does for entropy. So I can start by putting 4 atoms into this 4 by 4 box, and you'll notice they have some room to move around, but not very flexible. Now, if I increase the size of this box, I still have these same 4 atoms, but because there's more different places they can be, we would say that this is an entropically favored system. It goes from a more organized state with fewer options to a less organized state where there's more different arrangements. Now, let's go ahead and examine what this looks like more numerically to see how the Boltzmann formula works. So let's go ahead and start by figuring out how many microstates there are for each system. So for this, we can go ahead and steal some equations from probability theory. And if I'm able to put multiple atoms per box, the formula here is pretty easy. It's going to simply be the number of boxes, so the number of places that each atom can go, to the power of the number of objects. So you can imagine if I'm looking at this first system, there's 16 boxes, which means there's 16 places to put each of these atoms. So it would be 16 times 16 times 16 times 16. And we can do the same thing for our larger volume space, where there's now 24 boxes. So that means that we have, for the initial system, somewhere around 6.6 times 10 to the fourth. So about 66,000. But for the final system, it's now closer to 330,000. That means there's now 50 times as many ways to organize these 4 atoms in the larger container. So we'd say that this final system has a lot more entropies. There's more ways to place those 4 atoms. But notice, while I'm increasing the size of the system by 50%, the number of microstates increased 5-fold. So again, there isn't just a nice one-to-one correlation. And this can make measuring the entropy of a system kind of complicated. Now we can also look at this if I'm in a more realistic case, if I'm only allowing a single atom per each of these boxes. At this point, we have to go ahead and remove all of the states that have multiple objects per box. And you can do this by taking the number of objects and taking the factorial. So if you only have one object, There's no repeats. If you have two objects, two of those states are going to be repeats. But if I've got 4, now it's 4 factorial, so that's going to be 24. So I have to go ahead and divide out by any of these repeated states. So that means if I'm looking at the corrected system, that for the initial state, I'm looking at around 3,000 microstates, and for the final system, closer to 14,000 microstates. So again, notice because I'm dividing both things by the same number, we still have a 5-fold increase in microstates for that expansion. So again, what we're really seeing here, and the bit I want to kind of make sure you focus on, is that when we're looking at things like compressions and expansions, this is a very easy case to see where entropy favors. Entropy is always going to favor systems with larger volumes. Similarly, it will also tend to favor states with higher temperatures, because the more temperature I have, as we saw with the ideal gas scenario, the more different velocities I can have, the more different arrangements of the system. And we can encapsulate this with somebody we haven't seen for a while, and this is the Boltzmann distribution. And this is the idea that how likely we are to have a molecule in a given state is going to be proportional to the exponential of the negative energy over the temperature. So at very low temperatures, it means we only really have molecules in the ground state. At high temperatures, we occupy more of those excited states. And that means that if I have at higher temperatures, I'm occupying more excited states. That means that I should expect to see the microstates increase immensely as I get to higher temperatures. And this is the reason why entropy tends to favor heating of objects, because you want to, the higher temperature you are, the more microstates you have, and that's going to be very entropically favorable. One of the big things is that we'll always see this increase with temperature, but this increase is going to be much slower at higher temps. So if I have something at a relatively low temp, that means I'm going to be very organized. So any additional increase in heat will greatly disorganize the system. But if I'm already at a fairly warm temperature and I add the same amount of heat, that means I only increase the entropy just a little bit. I am indeed getting access to one more state, but again, notice that the system was, the relative increase in entropy is going to be relatively low. This is one of the reasons why if I have an object at high heat and low heat, or high temp and low temp, and I put them next together, I would rather go ahead and remove some energy from the high temp and put it into the low temp, where it will become more readily disordered. And this is what really drives the idea of heat transfer from hot objects to low objects, that it will benefit the lower temp system to have more energy, much more than it benefits the high energy, because that's what's going to make sure everything is the most disorganized. Now, again, we can go ahead and look at this again from a little bit of a micro scale perspective. And let's go ahead and look at a very simple system that actually encapsulates some molecular systems relatively well. So let's say I've got 4 molecules, all in their ground state energy. So they're all very stable and they have almost no energy. So this is often what you're going to see at a temperature of 0 Kelvin. Everybody's in the ground state. That means that the entropy is 0 because there's only one way to organize it, one microstate. Now, let's say I've got some empty excited states with energies of 1 and 2. So if I put one equivalent of heat, I have enough energy to excite one of these molecules up to the excited state. So that means that I'll have one molecule in the excited state and 3 in the ground state. But it turns out there's going to be 4 different ways to generate this, because I could excite molecule A, B, C, or D, any of them. So that brings my microstates up to 4, which we can then use to calculate our entropy as about 1.4 times the Boltzmann constant. So again, the microstates went up by 4-fold, but we had about 1.4 equivalents of entropy increase. Now let's see what happens when I take this already excited system and add the same amount of heat. So I can add that same amount of heat again, and I can excite the molecule that's already excited. And so now my total energy is 2, and I have 1 in the doubly excited state and 3 in the ground state. And again, there's going to be 4 ways to do this based on which molecule is in that extra excited state. But we could also imagine that I could go ahead and instead of exciting that already excited molecule, I could excite one of the ground state ones. And this means that I have an extra set of configurations. And if you do the numbers, it'll turn out there's about 6 different ways to generate this. So if we add these together, it means that this energy of 2 has a microstate of 10. Plug that into our Boltzmann entropy equation, and we find that the entropy is about 2.3. So notice, if I go from the ground state of energy of 0 to energy of 1, I have a 4-fold increase in microstates. But if I add that same amount of energy, I now only have about uh, a 1.5 increase in microstates. So I'm still becoming a lot more disordered, but not as much as if I'm a lower energy. We can also see this from the entropy's perspective, going from 0 to 1.4 on the first time, so an increase of 1.4, but only an increase of 0.9 the second time. So again, about about half as much as I had from that first equivalent of energy. And this really helps drive why we see this idea that that low energy systems are giving them energy is going to be a lot more beneficial than giving that same amount of energy to high energy systems. And this will help energy spread out to try and give as much energy to everybody as possible to keep the system as relatively disordered as possible. So next time, we're going to go ahead and return to our thermodynamic perspective and go ahead and look at how entropy is moved around systems, mostly as heat. Until then, take care.